See, we got to create what we call a phase shift, something that holds the magnetic field when the AC drops to zero. And I can show y'all on some relays. So normally what we do on this, of course, is we just get magnetic wire. Y'all know what magnetic wire is now, right? It's just a wire that has extremely thin insulation, so we can get really good magnetic coupling between the conductors.
Magnetic wire for?
So it has really thin insulation on it. So we can get really good coupling between the conductors, right? So I passed it around last class and showed y'all that loop of magnetic wire. And then what we do is we just wrap it around a chunk of metal. And what does metal do? Concentrates the magnetic field. So we try to wrap this as good as we can. We wrap it in the same direction so the magnetic fields add up, right? You understand? And then all we do is we come in and we put some DC on this, and then we come up and create a magnetic field. Now it'll be hard to do with this one. I'll have to use a regular magnet, but I'm looking for a piece of metal I can pick up. Stay right there. I don't know if this guy's got enough strength. I don't know where my big one's at that I made. I didn't think it would do that. I want this power supply to put out enough energy to allow me to do it, but we'll try it. So you got to use a lot of turns of wire. Why do you got to use a lot of turns of wire? Well, not to create the field. So normally you see these electromagnets, they'll have thousands of turns of wire, right? You understand? So I could take one loop and I could put 1,000 amps through it and I could create a lot of current, but the wire would have to be a really big gauge, right? And take a lot of current. If I double the number of loops, then I can lower the voltage. I could half the voltage and still get the same magnetic field as long as I wrap the wires real close together. So what you got to understand, the only resistance to DC, the only resistance the DC sees is the resistance of the wire. So if you have a real low resistance, it's going to create a lot of current to get the magnetic field. If we use a lot of wire and wind them really close together and wire them in the same direction so the magnetic fields add together, then what we can do now is we can run it on a lower voltage DC, and it requires less current, right? You understand that? So when you get into these electromagnets, you're going to see a lot of turns of wire if it's DC. Now AC, there's a feature of AC called X of L if you've had AC, where the opposition of a coil varies with frequency. So an AC coil will not have as many turns as a DC coil, because not only does it get the resistance of the wire, it also gets the reactance of the coil against a change in magnetic field. But the problem is people, if you got an AC coil and you put DC on it, you're going to burn stuff up, right? Because it don't have the X of L. If you take an AC, if you take a DC coil and put AC, it's going to have so much inductance it won't create a strong field. Does all that make sense? No, if it don't, you'll run it when you take AC. So in AC, out of a coil of wire, we get another form of opposition. We call it reactance, which is really neat. So anybody that tells you AC and DC are the same, they're not. AC causes phase shifts. AC, we have to deal with reactance, which is, and it changes with frequency. So when they design these AC coils, they design it around a certain frequency. If you go above that frequency, the strength of the field goes down. If you go below that, the strength of the field might go up, but now why is it going up? Because you're having to supply more current. I think this is too heavy for my little magnet, so I'll have to find something else.
You want a paper clip?
Yeah, you got a paper cup? So all I did on this, where I could make a connection to it, is I just took it and scraped off that pane, and that's the problem with the magnetic wire. To get the coupling, the wires are so the insulation is so thin, it's really easy to strip off. So that's a lot on a lot of motors. They'll take the windings on the motor and dip them in a polyethylene type lacquer. So that way things can't rub against them. So all it takes is just a little thing rubbing against it, right? You understand? So if you ever look inside a motor, they've got those coils tied down really, really tight because the motors are trying, the coils are trying to push each other apart, right? You understand? Because they're generating the magnetic field moving in the same direction. Magnetic field's moving in the same direction. If you can couple them close enough, they'll combine, but they're also trying to do what? Push themselves apart. And that's why transformers hum. People's always wondered what makes a transformer hum. Well, what makes a transformer hum is those dang wires are trying to do what? They're literally trying to push apart from each other. So they really, really got to take those things down. So what we can do with this is we can create a magnetic field, right? But we're doing this electrically. But what's nice about this over a permanent magnet is I can do what? I can turn it what? Off and on, and I can control its strength. So the more voltage I put on it, the stronger the magnetic field. The less voltage I put on it, which means current, because we're dealing with R of the wire, right? You understand that? And I is equal to V over R. Then the weaker the magnetic field, which gives us the ability to regulate AC. And y'all know if we pass a magnetic field, if we pass a wire through a magnetic field, it'll induce a voltage into it, right? Everybody's seen that before, right? Y'all seen this little thing over here. Okay. And what determines the amount that I induce in there would be the speed of the motion, the strength of the magnetic field we're going through, and then of course the number of what? Number of turns. So what we're doing in your car or and this is the way we generate our probably 99.9% of our power is generated by passing a conductor through a magnetic field. But what we can do with that magnetic field is make that magnetic field variable, right? You understand? So what that means is we can regulate the output of the generators. So your car's got a regulator on it, right? So when you speed your car up, your alternator wants to put out more voltage, but your regulator decreases the strength of the spinning magnetic field, right? You understand? And if your car tries to slow down, your output of your alternator tries to go down, but your regulator sees that and puts more strength in the magnetic field. So now we can regulate the output. Unregulated, we'll use that for something else. Well, what's nice, since we do that, we have these little things right here, and that's why I brought those over here. We can make these extremely small relays. So this is a relay, but it's actually a reed relay, which means on our coil, it's not actually picking up a contact, it's wrapped around a reed switch, right? You understand? And then when we put it on that, it closes the reed switch. So now we can get these little old tiny relays. So this is a relay right here. This one I would have to look up. In fact, both of them I have to look up. So these are two, but they're reed relays. So now we can come in and generate these relays. And why do we like to use relays? Well, relays, I can put DC in and get what on my contact? AC. Or I could put low DC in and get a higher voltage DC through the contacts, right? Y'all understand that? So these are reed relays right here. What are our PLC? In fact, our PLC that says it has relay outputs is actually having some reed relays. These are the encoders that we bought. These are incremental encoders, so they don't give us direction. So all we could get out of these right now is position. But also, what's nice about an optical encoder is it can give us two things. What's the two things it can give us? An optical encoder. What's the two things it can provide to us? Yeah, at least position and speed. A quadrature encoder, we can use it for position, speed, and what? Direction. But every one of them we can use the time for the pulses or the frequency of the pulses. We can do that to calculate speed, right? You understand? And then we can use every one of the pulses to give us a certain position. Are you okay? So what I've done here is I've combined both of them, and hopefully this works. And we're not doing it for position right now. It'd be real hard. That takes a pretty good deal of electronics. So what we're doing is we're using a through the beam, or what the book calls a direct scan. Now we use these all the time, so it makes sense that they would come out with a unit, we call them optical interrupters, that has a through the beam sensor in it. There you go, good. So when you look at this, you'll see one called E and one called D when you look at it at the top. So E is the emitter and D would be the what? Detector, and it's built inside that unit. So what I've done, if my camera will focus in, is I have a encoder here. The encoder is just a wheel, but we got to combine it. So when we say an incremental encoder, we combine two sensors, and what you're going to find out, a lot of these sensors combine two sensors or two sensing elements to give us a sensor, right? You understand? So when we say an incremental encoder, we just can't have the wheel. The wheel would mean nothing, right? You understand? Unless we spun it through something where it can pick it up. We can do this two ways, and I need to go add that to the PowerPoint because I don't think, and you'll see these used a lot in the industry when you're in a very harsh environment. Now, encoders are usually pretty immune to stuff because we seal everything up. So if I was to go on the internet and if I was going to look at encoders, what you're going to see is oh, this is not the internet, Rich. So you're going to see these things all sealed up, and all you have is wires coming out of them. Since they're all sealed up, it means what? It means we can run these things in real harsh environments also. But we do have extremely harsh environments. So quite a few years ago, they added something to our vehicles, these automatic braking systems, and also what do they call it? Anti-slip, anti-lock things. So what they had to do is they had to come up with some type of sensor that was very, very reliable that they could put out on the wheels of this car to determine when you hit on the brakes, does the wheels lock up and the car is still in motion. And if they sense that, what do they automatically start doing? They automatically start pulsing the brake. Well, what they did is, of course, they're using encoders, but they're not using optical encoders. They're using what we call variable reluctance encoders. So variable reluctance encoders, oops. Sensor, there we go. So I don't know if there's going to give us a picture on this, but that's a good one right there. So the way the variable reluctance encoders works is it spins magnets. North, south, north, south, north, south, north, south, north, south, north, south. This is a really good picture right here, and it doesn't have very much. So what we do is we have a north, south, north, south, north, south. And what happens is when these blades spin around, it goes through that slot and concentrates the magnetic field. Well, when it concentrates the magnetic field, it causes the magnetic field with this coil wrapped around it to change, and as soon as it changes, it induces a pull. Right? You understand that? So every time one of these blades fly by, I get a pulse out of this coil. And this is a variable reluctance. This is what they use on the cars, guys. This is what's out there on the wheels. They don't use these optical encoders. These guys are extremely rugged. They don't depend on this little old tiny blade thing that we're looking at that's got all the blades on it. These guys they're all metal. There's nothing plastic about them. They're all metal. And so now what we do out there on your wheel, it's got a blade thing that's spinning around, and then this guy sends back pulses, and we use that. I don't think they use it for speed. I think they still pick up the speed off the transmission, the speed of the car off the transmission. But when you look up anti-block systems, they're probably gonna have this thing out there. They put it on your wheel so they can determine what. Yeah, but if it locks up and the car is still in motion. So, but it's just an encoder, and it's an incremental encoder. So we can do two things with this. We can get speed off this, or we can get what? We can get position. Now they're not really using it on that for position. They're using it for what? Speed. So these guys were around long before the optical encoders came out. The variable reluctance has been around for a while. So what I have here is I have these guys this set up. And we'll look at an oscilloscope, because what advantage does an oscilloscope have over a meter? Yeah, you're actually seeing voltage relative to time. Your meter averages everything out. So let's see if this works. I hadn't used it in a while. So here's my through the beam. So what happens when this thing right here spins? It breaks the beam. Every time the light comes through, it lets the light come through the detector, and every time the plastic comes through, it blocks it, right? The encoder is not perfectly level. And also the motor doesn't have enough commentators on it to run extremely smooth. So this is what we're getting back. And each one of those pulses will represent a watt. Let me see if I can figure out how to. This is a storage scope. I just got to figure out how to do it. This is a really good scope. I'll probably do it later on. We can simulate this with this guy right here. Because all it's doing is giving us a series of pulses. So we could figure out the speed, guys. What would the speed be? What would we need to know? Well, scopes don't measure frequency, they measure time. Unless you got a digital storage scope. We got digital scopes available, and they're computers. The digital, but you can set those things up to not only give you the period, you can also get the time, the frequency too. So what we do down here, if y'all can see, is I got it on 1 millisecond per division. So if we just get kind of an average in the center, that would be 1, 2, 3, about 1, 2, 3, about 3.5 milliseconds. for 1 pulse. So how fast would the motor be going? Even though we're not on motors, we're doing. Anybody guess how you had to figure that out? Yeah, 3.5 milliseconds. Wait, let me redo that. Yeah, we'll use 3.5. 1, 2, 3. In fact, trying to find the speed. Actually, it's less than 3.5. Let's use 3 milliseconds to make it easy. Now, the first thing I would do is this is per pulse. So the first thing I would do, I would take 3 milliseconds, and I'm going to multiply it times 8. Anybody tell me why? Yeah. There's 8 holes in there, because we're not trying to get this thing in seconds, we're trying to get this in RPM. So what I did is I took the time for 1 pulse, and I divided it by 8, and that would give me the time per revolution, right? So what does that give me? Huh? Yeah, so we got 24 milliseconds per revolution. Okay, so what do I need to do now? Now somehow we got to get first of all we got to get from time to frequency, because RPM is a frequency, right? 24 milliseconds is a time per revolution. So how do I go from time to frequency? Okay, so my time per revolution, my frequency per revolution would be 1 over 24 milli. What does that give me? 41.6 revolutions per what? Second. Good. So now I need to get this into revolutions per minute. Yeah, so I'd say RPM would be equal to 41.6 times 60. And then this would give me the speed that this little motor is actually running. 2,500 RPM. Good job, guys. We got a sample of the one sample of the Siemens Level 1 certification, and this almost exact questions on it, or trying to take the output of the encoder and relative that to time. Does that make sense? Thank goodness with a PLC it's a lot easier, and we'll show you how to do that later. So first of all, we get the what? The time. Then we multiply that by the number of pulses we get out per revolution, right? And then that gives us the time per revolution. Then we do what? We take the reciprocal of it, and that gives us the frequency per revolution. And then we multiply that by 60, and that actually gives us revolutions per minute instead of revolutions per second. Okay? But somehow I've got to get this over to just make sense. because the average person is not going to know anything about this. All they're going to look at is a display somewhere that says what? 2,500 RPM, which is pretty fast. But you can see, we can definitely get speed off this thing. All we're doing is dealing with different times, right? So if I slow it down, the time goes up. If I speed it up, there we go. That it's moved out there. The time goes down. Oh, I don't have it hooked up to the other side. So that's 15 volts. I don't know what this motor's rated at. DC motors, basically you can run these things until they sling themselves apart. DC motors. AC motors, the speed is depending on what frequency you apply to it. So the first labs we're actually going to do is on position sensors. I'm sorry, proximity sensors. We don't have any labs on position sensors, but one day maybe we can get time to go back over to the manufacturing line. Both the manufacturing lines use a potentiometer as a position sensor. And then it's got an ultrasonic position sensor on it also. But where's my? Oh, just about all the PLCs. I don't think the 1100. I don't think the I'm sorry, the 1000s we have down there support optical encoders, but the 1100s that we have do, and the new Siemens that we have do, because these are very, very popular. So we talked about push buttons, limit switches. Everybody okay there? Read switches. And like I said, I'll find my magnet and trip those off. We talked about photoelectric. This is where we're at right now. Through the beam, right? Everybody okay there? Book call it direct scan. I'm pretty sure the book calls this retroreflective. I'm not really sure. Retro scan, yeah. So this is what I learned it at. If you look it up, I think you might can look up both of them on the internet. You get pretty much well the same thing. So if you walk into the bookstore, you run into one of these guys. How does it know when you walk in there? You hear that thing go beep. But if you look at one side, it's got the transmitter receiver, and on the other side, it's got a retroreflector. And that's what you're walking through down there. So now y'all are going to start looking for it. Now y'all notice it.
We hear the beat sometimes.
We had I think I told you about the one at US Steel through the beam we had out there on the wire yard, where the line crew stored all their cabling. A guy came out there. Well, they don't know if it was a guy, but it probably was. A guy had came out there, and while he was on shift, and they had one of the big spools out there, and he took the end of it and pulled it through the chain link fence before we put it out there. And then he came back at night and hooked a cable up to it, and ran that thing and unrolled it down, and then rolled it off on the side of the road out there. And then he'd come back and he'd cut off links and carry the links on. So they I don't know if they caught the guy or not. Hopefully they did. But that's when we put that big through the beam sensor out there. So it ran the whole length of that fence. And of course you couldn't see it because you couldn't see the thing. And then we also ran a real fine wire down the entire length of the fence. So and it was really fine. It's hard to see where if somebody came in and did wire. They cut it, they would cut the wire. We did that.
Do we have one of those on the line and something?
Yeah, we got several on both of them.
Okay, I know where they got acrylic blocks and metal blocks.
Yeah, there's a through the beam. I'm sorry, there's a not a diffused. You said, do we have a diffused?
Where is the diffuse?
There's a diffuse on the primary magazine, the feed magazine that feeds the blocks on. There's a diffuse sensor on the bottom. You have to get over there and look to find it. It's actually pointing up, and what's it doing is it's detecting when the blocks are empty. We found out we had a problem real fast, and we might can adjust it. We just never have got around to it. Is some of the blocks have RFID tags on them, and the RFID tags that they decided to use are black. So every block you can put in, you can put it in any way you want to. If you put it in sideways, it'll reject it. If you put it in, and the metal blocks don't have a top and a bottom, but the acrylic blocks do. But those blocks that's got those RFID tags on them, if you put those black side down, they'll tell you that the magazine's empty when they fall down, because it's a diffuse sensor. And what's one of the problems with diffuse sensors? Yeah, the color. I haven't looked to see if there's a threshold adjustment on it. If it's got a threshold adjustment, then odds are we can adjust it to see that the ones with the RFID tag on it. But I don't know why we'll do it, because it's a good problem, right? You understand that we could put in there when we troubleshoot it, and you'd be surprised how many people go off and really get off on a tangent when it was just an obvious thing from that sensor. So that's the only diffuse sensor I know of. The Festo line has a diffuse sensor all over the place. It's got the robot's got one on it. It uses it to sense the color and find the spring and find the cow. The little cradle, when it comes off the conveyor belt and it falls down, and it sends a signal saying there's one there, so the robot knows to pick it up. That's a diffuse sensor. I don't know what they call that. It's the robot, the robot across the top. It's got a diffuse sensor on it too. It's above the conveyor. It's the one that transfers it from the process station over to the buffer station. That robot's got a diffuse sensor on it, and it's broke. The fiber's broke, but we don't ever use it. That comes into play if you split the line apart. If you split the line apart, then the robot will sort them for you if you run that program. But we don't ever split the line apart or have it, so we have no need for it. So that's why we haven't got around to fix it. There's both of them. The Festo line has a bunch of these through the beams. It uses a through the beam in the distribution station where you put the cylinders in. It shoots the beam across. It uses a through the beam over on the conveyor belt to determine when it's at a position where it can open up the gate. So it's got a lot of through the beams. So the Festo line has got all three of the sensors on it. It's got all three of the photoelectric sensors. It's got through the beam, it's got diffused, and it's got retroreflective. The Amtro line has diffused and through the beam and retroreflective too. And then this is the optical interrupter that I just passed around for you. And this is nothing but a through the beam sensor. We got to put some external things on it. So if you take my unit and flip it upside down, you'd see some resistors in there. So you have to calculate the resistors depending on what voltage you put up here and how much current you want to allow to flow through the photo transistor. And then of course you do the same thing here. So the more voltage you put on there, the bigger the resistor would have to be, because you want to put the same current through this guy all the time, right? So, if we know the voltage drop across the diode when it's forward biased, then we know the current flow that we want to put through it, and we calculate the size of the resistor. So if you flip mine over, you can see two resistors. So the actual interrupter would end, and you'll run into these a lot because they're made in. So the actual interrupter ends right here. So this would be the actual interrupter, and that's why you see the 4 wires coming out the bottom. 2 is for the detector. So there's the one that's labeled D, and then 2, the other one would be the one they labeled E. Now, to forward bias these things, you got to forward bias them. So if you also look, you would see a little plus on which side you're supposed to hook the positive power to, because these guys have to be biased, and we talked about that. And like we talked about in DC, we touched on it a little bit. Resistors in DC and resistors in AC, they do one thing. They do what work do? They produce heat. They drop a voltage and produce heat. But when you get into electronics, the primary use of resistors is to bias these things, to set the operating characteristics of the device. This is Hall effect. Now, hopefully my Hall effects work. They're really, really neat. So Hall effect does not actually, these are electronic. Number one, they're electronic. So we have a Hall effect sensor, and normally you got a minus and you got a minus. We use the same supplies, so this is kind of misleading. It looks like here we're running off 2 supplies, but in actuality we run it off 3. I mean off of 1 supply. So what we have on most Hall effects, and they vary in size, is we're going to have 3 wires coming off of them. And they look like transistors, by the way. So when you pick up a package, and it's got 3 leads popping out of it, it does not mean it's a transistor. It means it's a device that requires what? 3 electronic connections. That's all. 3 connections. That's all that means. 3 connections to it. These packages, by the way, these are open technology packages, and they're given names. They're called TO packages, the transistor outline. But you'll see integrated circuits inside these things. You'll see voltage regulators, which are integrated circuits inside these things. You'll see transistors, SCRs. You'll see triacs. So a lot of different electronic devices go in here. So the Hall effect is an electronic device, but it's got to be powered up. Now what the Hall effect does is the Hall effect can detect a magnetic field. That's what it can do. Now we can fake it out sometimes and put a chunk of metal in it, right? So here we have a magnet, and then we have a Hall effect, and the magnet's on one side and the Hall effect's on between it. So what happens when the ball moves through there, the strength of the magnetic field, what's the word I'm looking for? Well, it does trip it, but it concentrates. It concentrates the magnetic field, and that's what the Hall effect is seeing. It's seeing the concentration of the magnetic field caused by the metal. It's not sensing the metal, right? You understand? The Hall effect does not sense metal. The Hall effect senses a magnetic field. We have 2 types of Hall effect. We have one we call latching, and then we have one we call an analog. So an analog would actually give you a voltage out that indicates the strength of the magnetic field that is detected, which is pretty neat, which gives us now. Originally, when we came out with, it's very dangerous, especially in industrial applications, to measure current. So how do we measure current? How do we have to measure current? We have to break the circuit and make the current flow through our meter. Y'all understand that?
Yes.
Okay. But when that current flows through a wire, it generates a magnetic field. The strength of the magnetic field is directly proportional to the current. So if I can measure the strength of the magnetic field, then I can translate that into a what? A current. AC is real easy because what do we need to do to induce a voltage magnetically? What do we need? What do we need? Well, okay, we need a conductor. I usually don't put that first. First of all, I say we need a magnetic field. No, we don't need if we needed a power source, we need an energy source, right? You understand? So we can't create energy. We cannot create energy. All we can do is what? Change its source.
Okay, you got those wires, and you put something far.
We put some type of energy in it. So the magnetic field is a form of what? Energy. So if I pass a conductor through that energy, it's going to induce a voltage into, or an EMF into the wire. Now what determines the amount? Okay, wait, let's get through with this first. So we got to get a conductor, right? And what do we have to do? We have to cut it. We have to move it through there. So what we're doing is we're taking two forms of energy. We're taking motion and then the strength of the field. So we got to have motion. Actually, I like to use relative motion. What we have to do, and we just can't say motion, that motion has to deliberately make that conductor cut through the lines of force. I like to say relative motion because then you'll understand how a car generator works. What we're doing here is we're moving the wire through the magnetic field. That's not the way your alternator works. Your alternator moves the magnetic field through the wire. So what's actually spinning is the magnetic wire, is the magnetic field. Okay. And we couple DC through it through slip rings. So what determines the amount? Yeah, let's go through this list. Right down the line. 1. The strength. Not the size, the strength. And what's next? I'll be trying to say this the whole time. Yeah, a number of conductor loops. And they got to be wound in the same direction, right? Because what you want is you want the EMF produced into each one of them. So every time we swing through that thing, we're ending up with this right here. And each one of these would represent a winding. And so what happens is the more windings we put, what happens when we hook battery or put DC sources series 80? Their voltage does what? Adds together. So every winding gives us a little tiny EMF, little tiny, but we use a lot of loops. And what's number 4? It determines the amount. Oh, I'm sorry. What's number 3? What's number 3? Yeah, the speed of the motion. Now, most people want to say the size of the wire. The size of the wire has absolutely nothing with the amount of EMF you get. The size of the wire determines how much current you can get out of this EMF, right? You understand that? Because if we have a lot of resistance in that wire, then if I try to load it, then the wire will drop the voltage that I'm trying to produce. So the size of the conductors that we use, and of course how we wind the winding. So what we do is they have what they call lap winding and wave winding, different ways we wind that. So what we do is we take multiple conductors and we hook them in parallel, multiple loops, and we hook them in parallel to increase the what? Current. And then we when we have them wound in series to produce the voltage. Right? You understand that? And then the size of the wire would determine how much current we get. But we can't use just one loop of wire because what we wouldn't get any voltage out of it, right? You understand? So if you ever look at these generators, you're going to see a bunch of loops of wire. So what gives us all this? Well, AC gives us all this. So in industry, you're going to see one of two things measuring the current. You're going to see what we call a shunt. Y'all know how we measure current? Meters can't measure, the actual meter element cannot measure current. So how do we measure? How does a meter measure current? No, we're not using amp count. We're talking about a meter. How does it measure current? Well, it don't. It measures voltage. So what we do is we take this current and we make it go through a resistor that has almost no resistance, maybe 1 milliohm. No, this is inside the meter. And then what we do is we measure the voltage drop across that. And then your meter interprets that voltage drop as a what? A current. So you'll go out into industry and you'll see these big old chunks of metal, and you'll see two little old tiny wires coming over it. Well, the two wires coming through is for your meter, right? You understand? And that's the shunt. AC though, AC gives us every one of these. AC gives us every one of these. So you might come over there and you'll see just a loop, and you'll see the wire running through the loop. We call these current transformers. So what happens is this change in magnetic field for that wire induces a voltage into the current transformer that is directly proportional to the what? To the current. We're not measuring the current. People get confused. We're not measuring the current. The guys measures the what? The strength of the field. That's what they're measuring. And then they translate that into a what? Current. So we have these things called clamp-on ammeters, which basically is nothing but this. But now we can open the clamp, we can put a wire through it and close the clamp, right? You understand? And now our clamp-on ammeter is a clamp-on. Is it an ammeter? No. It measures the strength of the field. A true ammeter has got to pass through the meter, right, or through the shunt. Everybody understand the difference? Well, we got this Hall effect guy. This Hall effect guy it don't need relative motion. It's going to measure the strength of a magnetic field. So now if you're willing to pay for it, you can get a clamp-on ammeter that'll measure DC. And how does it do it? It does it with a Hall. It's got electronics in it that uses Hall effect.
Let me make sure I understood what you said. A meter does not measure current. It actually uses a small resistor
called a shunt
and measures the voltage drop
across the shunt. Yeah.
And then,
yeah, but it's internal. You don't see it. You don't see it. If we pop the meter open, I don't know if I got one of the Sperry's here. The low current side is gonna have a bigger shunt. It's gonna be like 100 ohms because it's got to drop you say 100 ohms, that's going to drop a lot of voltage. But your low current side is going to be dealing with milliamps or microamps, right? You understand? And if you put 1 milliamp through a 100 ohm resistor, it's going to drop millivolts, right? You understand? But if I'm getting up into the 10 amp range, then these shunts are going to be pretty good size, right? You understand? And we can open up, we can see the high current shunt. The low current shunt is probably just a trace on your board. You don't even see that. Or it might even actually be a physical, a really high.
so you say that shunt or whatever is about 1 milliamp in a meter. Is that what it is?
No, for low current. The lower the current you have to measure, the bigger the shunt has to be. That's all the shunt is a resistor. But normally that resistor is just a resistive wire. Instead of using copper, you'll use something like nichrome or something like that. It's a wire that has more resistance. And then if you've got a conductor that has more resistance, then you can do what? You can reduce the size of the shunt. But out in industry, what you'll see is they've got to get that over to some meter somewhere. And they don't want to run the current through your meter on your panel. So what they'll do is they'll have a shunt out there. I mean, it's a physical shunt. And then you'll see two little wires coming in and connecting to it because all it's doing is measuring what? A voltage. So you'll see an amp meter. We call them amp meters, but they're little voltmeters, and we just put the scale as what? Amps. Used to, you had what we call standard, which we had a 50 millivolt movement. So the meter, if it saw 50 millivolts, it would give you full scale, right? 100 millivolt meter movements. These were the magnetic meters. So 100 millivolts, they'd give you full scale, and then you just set the scale up to whatever you need. So all they do is they just set the scale up, to whatever you need. I don't know. I might have a shunt in. I tried to carry one around. And I don't think I got a spare in here. We do have some clamp-ons. But since they came out with this electronic circuit that we call the Hall effect, it gives us the ability now to have a clampometer that can also measure what? Can measure DC. I got a 50 amp gun. I think it's 50 amps. I think it's 50 millivolts, 50 amps. You can calculate that resistance. But that means when it saw 50 amps, it would drop what? 50 millivolts. So if I ran that into a 50 millivolt movement, then I could set off the scale on the movement, right? You understand? Make it appear to be measuring current. But the meter's not the meter itself. The meter movement. I'm not talking about the meter. The meter's measuring current. Because the meter is going to be that unit that you're holding in your hand. But the actual devices that measures, that actually converts it over is going to be, all it's looking at is voltage. By the way, your meter movement, no matter what your meter does, the electronics that's doing the measurements, all it measures is voltage. That's all it can measure. Even when you got it on ohms. So when you flip your meter to ohms, it turns into a voltage. It turns into a current source. So the way most digital meters work is they try to output a precise current, like 1 milliamp. And you put that out there, and the voltage raises. The meter automatically ranges up and puts out the amount of voltage that's required to cause what? 1 milliamp to flow, and then it interprets that as what on your meter? Ohms. So one of the things you do on the meter, you can measure it. So you can get a voltmeter and hook it up to your ohm meter and flip that sucker over, and your other meter is going to read a voltage. Because that's what it's outputting. It's trying to raise it raises the voltage until it gets what? A certain current to flow. And it's usually like 1 milliamp, because 1 milliamp don't hurt a lot of things. We had a transmitter, one of our transmitters that would run a crane out at US Steel. I think it was made out by GE. We had some GE and Fanuc remote control cranes out there. And you couldn't check that little fuse with an ohm meter. If you tried to check the fuse with an ohm meter, you'd blow it. Blow the fuse. Now, it didn't hurt the meter, but it was rated at such a low current that when that meter put out that 1 milliamp, it would do what? It would blow the fuse. So what we had to do is we had to power it up and measure voltage drop across it. If a fuse is good, how much voltage should it drop? Huh? Yeah. Well, we can't say none. It's going to drop some because that's the way it blows. It's got to have an R or it wouldn't do what? It wouldn't blow. So your really, really low amperage fuses, they're going to have ohms. Your high amperage fuses, those are going to be way down in the milliohms, and your meter might not be able to measure. So that's the way a fuse works. A fuse blows from heat. How can it get heat? Yeah, it's got to have I square R, right? You understand? So every fuse is going to measure resistance. It's just that sometimes on your high current fuses, you can't measure it. But on these low current fuses, these guys that blow in milliamps and stuff like that, those guys are going to be ohms. You'll be able to measure that if your meter don't do what? Yeah, don't blow the fuse.
How many fuses did y'all change before you figured that out?
Well, it took us a little while. By the time I got there, the old hats, I started there, I think at 80 something. They said, don't check that thing with an ohm meter. So we didn't blow many after I got there. But they said, don't check that thing with an ohm meter, you'll blow it. Because we just put the batteries in and powered up and put it across it. So Hall effect, I've got a couple up here. Y'all go ahead and take a 5-minute break, and then let me see if I can get this thing to work. If I can figure it out. Oh, well, here we take 10-minute breaks, though, right? Because we don't do a lunch. This class gets out at, yeah.
I was supposed to say I might have to take an extra minute.
Yeah, I get my classes confused. Oh, somebody stole one of my LEDs. No, they didn't. I don't have an LED. Capacitive and inductive proximity sensors have no moving parts, no physical contact with the item being sent. Can be operated in dirty environments. Capacitive sensors can be obtained to detect solids, liquids, and gases. Inductive sensors detect only metal. That says ferrous metals, but it'll detect just about any metal. So it'll detect aluminum, but you got to get really close to it, right? It can detect some non-ferrous metals. So these are your capacitive sensors, and what you're going to see is we have two types, by the way. We have what they call a shielded and unshielded. This doesn't have an example of it. Let's see if I can get another slide. Yeah. So these are the ones they call shielded. These are the ones they call unshielded. You'll see the difference. What's the difference? Yeah, one of them's designed to flush mount. So we can literally, you see these like, coming through slides and stuff like that. They mount them flush. Which one would you think would have the most range? Yeah, the unshielded, because these generate a field out, right? Understand? These are going to be more selective, right? Yeah, because their field they generated straight up. Unshielded is out. So it all depends on what type of application that you're looking at. If you want it to be less selective, then you'll use an unshielded. If you want it to be more selective, you use a white shielded. If you got to flush mount it, guys, and things that have got to come passive, then odds are you're going to use an unshielded. I'm sorry, shielded. So these guys work off of AC. Both the inductive and the capacitive work off AC. But the problem is probably over 90% of the actual sensing modules are DC. But we can use devices called rectifiers, and very easily we can turn rectifiers into DC. I'm sorry, rectifiers are diodes that's designed to turn AC into DC. That's it. AC and DC. That's that backwards. And sometimes we do turn DC back into AC. A perfect example is this guy right here. This is called a function generator. Alabama Power gives us 60 cycles. If I want to change that 60 cycles to a higher frequency or a lower frequency, then we're going to have to usually do it. We're going to have to do it electronically, right? They used to. We had some induction heaters out at US Steel. We had them in the what they call the Curve Master. And what the Curve Master did, y'all know how an induction heater works. Anybody know how it works? Well, when we have a varying magnetic field and you got a chunk of metal, then it's going to induce a voltage into that metal. Now, what we get by with, if it's a solid chunk of metal, it's going to act like a short circuit to that transformer. So we get by with it on transformers by splitting that metal up. We slip it up in these laminated cores. But if you put a nice strong varied magnetic field across a chunk of metal, that metal is going to get hot. So we have what we call induction heat. We have induction furnaces where we take solid metal and put it in a varying magnetic field, and it's solid metal. It's going to induce that voltage into that metal. That metal is solid metal, so what's it going to do? It's going to produce a lot of current because it's basically short circuit, and it gets real hot, and it gets hot enough to melt.
Is that how they melt?
Well, we have two types. We have induction heaters, and then we have what they call arc furnaces. Arc furnaces is exactly what they say. Well, no, it creates arcs. Arcs creates temperatures hotter than the sun, up into 32,000 degrees. So that's why a lot of times if we create an arc on a contact, it'll weld it together in a heartbeat. Right? You understand that? But what if we put one electrode down in there that's extremely high voltage, and then the metal is up against the next electrode, and we deliberately create an arc. And well, that arc it creates is going to be up above 3,000 degrees, and that's going to cause metal to if you continue the arc, then the metal's going to melt. And that's the way arc furnaces work. And they make a lot of noise. They go.
Big old electrode that goes down.
Yeah, those are arc furnaces.
Yeah.
And they basically, and you can see flashes when you turn that sucker on. You see them suckers start flashing. If it's not sealed up real well, that's all it's doing. It's creating a high voltage arc. That's all it is. It's a welder, but the metal is welding is what you're putting together, right? So we have induction furnaces, and we have what they call arc furnaces. And then, of course, we got gas furnaces that actually melt it with gas, which was predominantly what U.S. Steel used. Their big cube offs. They used gas. They used oxygen. If you put enough oxygen with anything, it'll burn. So basically, in a cube off, which is an oxygen furnace, is you put enough oxygen in there to make the steel burn, make the metals do what? They burn, and of course, then they melt themselves. And that's the primary way we melt metals. Well, what they did on the Curve Masters, they use induction heating, and they would put the rails on a big old carriage. Well, they put a insulator between the outside of the vessel and inside of the vessel. They call them furnace, but they're lined. They have a lining of furnace, what they call usually furnace bricks or some type of layer that they spray in there. That's an insulator. It's like the shuttle. The shuttle uses insulating tiles in there, and the tiles on the shuttle. I mean, it's unbelievable, but it's maybe 1 inch, and you're going from thousands of degrees down to aluminum, and aluminum has a real low melting temperature. And we saw what happens when the tile breaks, right? It went through what was that, Challenger? Well, it actually disintegrated. No, the one that burned up, the one that flew into pieces. That was the Challenger one. One of them blew up on yeah, it blew up on takeoff because of the solid rocket boosters. But this is the one that disintegrated because some of the tiles came off the leading edge of the wings, and it got the aluminum and just did what? Melted everything in there, and then the wing came off, and the shuttle was doing thousands of miles an hour, and it just did what? But what these things did is they run on carriages, and then we would clamp the rails in like this, and it did 2 at a time. And then they would drop a big old induction heater over here that had wheels on it, and then they would move the carriage. And then they had big old air supplies. I think we ran like 200 psi that would purge it when it came out, so it would temper it. And then they poured water all over it to cool it down. But the air was actually what was actually tempering the metal. And what it did is actually harden the metal. These guys here run off 600 hertz induction heaters, and we had 60 cycle over here. Well, how did we get from 60 hertz to 600 hertz? Well, originally what they did was they had an MG set. So they had a motor running off 60 hertz, and they ran it into a generator that would generate to what? 600 hertz. At a real, it wasn't a real high voltage because it was a lot of current. Eventually, what they did before they shut NC down is we went from the MG sets because that was one thing that U.S. Steel couldn't rebuild. It was inside a sealed chamber, nitrogen chamber. So every time one of those MG sets broke down, they would have to haul it off. So they kept a spare and they had to come back and do all that rewiring. What they decided to do was to go to an inverter, so they electronically generated the hertz. So what the first thing you do is, what advantage does DC have over AC? Well, it's easier to electronically control. AC is almost impossible to electronically control. So anything you see that changes the frequency, the number one thing they do is they rectify it into DC. And then they use electronics to do what? Output a different frequency. And people want to understand why do we need negative and positive DC voltages? Well, you can't generate AC unless you have what? A positive voltage and a what? Negative voltage. So your car, your output of your radio, if you look at the output of your radio, it's outputting AC. We don't put DC on speakers. It'd burn them up because you lose XLL, right? You understand that? How does your radio give AC on the output? It does it what? Electronically. So, and we can do all kind of stuff. So the biggest advantage of DC is we can electronically control it. So what does this guy do right here? Well, it takes what? AC, converts it to a plus and minus DC, and now I can make it generate AC at any frequency I want up to the output voltages we have, right? You understand? So these function generators, they do. So that means I can power a sensor up off DC, and converting it to AC is no problem. My wife has a built-in inverter in her van. So she's got a 120 volt outlet in her van that I can hook up anything in there. How does it do that? It does it electronically. We call those things that's generator out there. We don't call them it's an alternator, right? Which means what does that thing try to put out? AC. Well, how do we get DC? Electronically, we have these diodes, these bridge rectifier circuits out there that we can do what? We can take AC and convert them to DC. So it's pretty easy to take AC and convert it to DC. We can do that with diodes. In fact, this guy right here, this is what we call a bridge rectifier. So I put AC on one side. If y'all look at it, I got AC on one, I got two plus and minus on the other. So I can go through that thing and I can end up with what? DC on one side. It's not pretty DC, but. So that means I can take a sensor and I can power it up off DC, but the actual sensing element requires what? AC. So these guys require AC. The actual sensing element, capacitors and inductors work off of AC. If you put DC on them, an inductor, if you put DC on an inductor, it acts like a piece of wire. If you put DC on a capacitor, it acts like an open switch once it's charged. If you put AC on a capacitor, then it passes relative to the frequency, right? You understand? So have no moving parts. Capacitive sensors can detect almost what? Anything. Inductive sensors, we use those to detect metals. So this could be a capacitive sensor. It's non-shielded. This could also be an inductive sensor. We don't know. But it's under the capacitive sensor catalog. So this is just, you don't need to know this, but this determines how much opposition the capacitor has to AC. And if you take DC, you'll learn more about this. I think Gary, you're in DC, right? AC, I'm sorry.
Yeah, it should be in DC again. Yes.
So we call the opposition to AC, we call it X sub L. I mean, here we call it X sub C. And the opposition is ohms, by the way. So when you get into AC, you're going to redo Ohm's law a little bit. Instead of saying I is equal to V over R, they should say I is equal to V over ohms. Because we have two types of ohms. We have resistive ohms, right? You understand? I read something the other day where the guy was called and called this resistance. This is not resistance. This is what we call reactance. Okay. We call this reactance. And what happens, it says the amount of opposition I get is equal to the reciprocal of 2 pi, so it's a constant, and what's L? Frequency times the size of the capacitor. And it's rated in Faraday. So it means if frequency goes up, X of C goes down. If frequency goes down, X of C goes up. If you have no frequency at all, X of C would be infinity, right? Of course, there's no such thing as infinity. It's going to be extremely high, extremely high. So what determines the amount of C is this guy right here. So what determines the amount of C? Size of the plate. So basically a capacitor, guys, and I can make a capacitor up here. It's just 2 plates. 2 conductors, we call them plates. And then you put AC across them. And what happens is when you put a positive polarity over here, it generates electrostatic field, which is going to interact with the electrostatic field that's going to be over here on the negative side at that instant. So we transfer current in and out of it. The best way I can tell you the way a capacitor works is if we have 2 buckets. And if you look at this as a plate, and then over here we have a resistor, and then we have an AC voltage, a pump. It's an AC pump, so the pump is constantly doing what? Back and forth, back and forth, back and forth. And so what would happen if I've got, it's going to just take it and do what? One direction, this guy here is going to fill up, then we reverse the pump, it's going to fill up. If you increase the speed of the pump, they're going to fill up faster. So that's exactly why as the frequency goes up, current goes up, right? You understand? Because the buckets are what? Filling up faster, and that's why it acts opposite. If I stop it, I have no absolute. So what you got to understand about a capacitor is there is no current flow through the capacitor. The current flow is what? In and out of it. So if there's no current flow through it, it creates no watts. Capacitors don't get hot. Capacitors don't get hot. Inductors can get hot because there's a path through there. An inductor has an R component to it. But capacitors, guys, there's almost no current through it. But what we do is we have to separate it by some type of insulator. And there's no such thing as a perfect insulator, so there will be some current flow through it, but it's going to be very, very, very low. If a capacitor gets hot, it means it's what? It means it's bad. If it's hotter than the ambient or the surrounding temperature, it's bad. So what can I do? I can adjust the size of the plates. So the bigger the plate, the more these static fields are going to interact with each other, so the capacitance goes up. The closer I can get the plates together, the interaction goes up. And then the next thing is what I use as this coupling between the electrostatic field. And that's the way they work. But what we're doing on these guys is we're not changing the distance, we're not changing the size. What we're doing is changing what is used as the insulator. And just about anything, guys, can act like a wall. An insulator if it's not touching the panel. So what happens is we come up here and we set these 2 plates. They're kind of set kind of weird. They're basically set like this. And they're real close together. So the electrostatic field is trying to do this. They're trying to couple together. And if I bring something into that field, guys, almost anything that comes into that field is going to change C. And if it changes C, it's going to change X of C. And X of C, if we can measure what's going on with X of C, then we can get this guy here to almost detect anything. Gases, they can detect gases, they can detect liquids, they can detect metals, because the metal itself is kind of like an insulator because it's not actually touching the 2 plates, right? You understand that? But it's a very, very poor insulator. So this guy here can detect almost anything. Solid, liquids, and gases. Now, what's nice about these things is they require almost no current to operate electronically for the electronics to generate the field. So unfortunately, it gets us it kind of breaks one of our rules that we learned in motor controls. What were some of the rules we learned in motor control? How many loads can you put in a rung? Not in a rung, in a line. Yeah, so we're fixing to break that rule. The problem we have with putting loads is that we start dropping a voltage, right? So if I came over here and if I came over here and I had two resistors, and let's say one of them was a 1K, and then the other one was a 1K, and let's say we put 10 volts across this, and we put them in series, and this is 10 volts, and this guy here is going to drop 5 volts, and this guy here is going to drop 5 volts. Okay. But what if I take that same circuit, and I come over here, and I make this equal to 2 ohms? What would be the voltage drop across this resistor right here? I'm waiting. So this is, huh? So what would be the voltage drop? Huh? No, it's 10 volts. This is not 5 anymore. I mean, as soon as I change that resistor, then the voltage drops in the circuit chain. Right? You understand? And this is a concept in DC that people don't understand. And I could go into DC and I could throw this question out, and they'll say, "Well, it'll still drop 5 volts because the current in the DC, current in a series circuit is constant." I say it's constant as long as you don't what? Change the circuit. As soon as you change the circuit, it's going to be constant for that circuit, but it's a new circuit, right? So how much voltage would be across the probably about 9.9 volts, right? Okay. Yeah, so what I'm saying is that, okay, so we say we can only have 2 loads we can only have 1 load. Well, the truth is we can have 1 primary load. If this other load we put in series has almost no opposition at all, and it doesn't make the voltage drop enough to affect your primary load, then yeah, we can put multiple loads in a rung. So these capacitive sensors, they only drop on 120 volts. I think when y'all measure that, they're going to drop like 4 volts. So what's 4 volts to 120 volts? Well, my load is still getting what? Huh? It's still getting 26 volts. 116 volts, right? You understand, which is well within the limits of operation. So I never get a load that says it's rated at 120. If it didn't have a range of voltages of where it's going to operate, that would be a problem, right? Especially here using Alabama Power. I mean, I can measure the 120, what's supposedly the 120 volts here, and you can go home and your 120 volts would be what? Different. Well, what if you had a load that was designed to run on 120 volts and it required exactly 120 volts? Then we'd be what? We'd be in trouble. So these 120 volts. So these guys are, we call these guys, these are usually called solid state limit switches. That's another word for them. So what we'll do is I can come over here. So by the way, anytime you see a solid state limit switch in motor controls, we put these things inside a diamond shape. And then they'll come in here and they'll draw the contact. And then they'll come over. And then I can come over here, and let's say I come over here and put a relay. And it's rated at 120 volts. That's what I was rated at. Well, one of the things you're going to do is you're going to measure the voltage drop. And these are 2 loads in series, right? You understand? But we're putting 120 volts across here. Well, we're not putting that much. I think we're putting like 108. Because we're going from 208. And we're going to divide by 2 we're actually getting more than 208. I think ours I can't remember, we'd have to measure. So usually we end up with about 108 volts over there. and this guy right here drops 4 volts, it still leaves us 104 volts over there to operate that relay. So we have no problem. So saying technically this would still be true, we're only putting one primary load per line, right? You understand? But these solid state limit switches, sorry, I'll finish up. These solid state limit switches, now where we get into problems if I start doing this. So how many limit switches could I put in series in a regular control circuit? I could put an infinite number because they drop no voltage. These solid state limit switches is going to get you in trouble because every time you add one, you got the voltage required to run the electronics, right? You understand that? So these guys drop a voltage. So what would you do to compensate for that? Well, you'd come up here and you'd put the solid state relay up here, and then you'll have it run a control relay. And then how many contacts can a control relay have on it? A bunch. And then we could come up and then we could use that to control it, or each one of them could run a control relay, right? Does that make sense? So you'll see that done a lot. These guys here have absolutely no moving parts. So when you get into 3, 4 limit through these things, you're trying to put in series with each other, then you're going to have a problem, right? Because each one of them is going to drop a voltage. They require that voltage to operate. So we have a voltage drop across them because we have current flow through them. So now we got volts, we got amps, we can create work inside our solid state sensor. So inductive sensors and capacitive sensors are going to have 2 wires. They're going to be 2-wire sensors, but they're electronic sensors. It's just that they require so little power to operate, and it drops such a small voltage, then we don't have to power these things up externally. We can power it up by the system itself. Are you okay? Any questions? So we're not going to use capacitive. We don't have capacitive. There's a lot of capacitives over on both lines. The ones that detect. So on the carousel, on both carousels over there, those sensors on the bottom, those are capacitive sensors. So I can put my hand out there and they'll trigger, right? It can see acrylic, it can see a metal, and you can trigger both of them.
One of them,
well, there's several of them. It depends on what we're trying to do. Oh yeah, I forgot about that one. Yeah, it's got one inductive. It's the one that finds home. If y'all remember when we was over there, it's the one that finds home. And then it's got another one down on the conveyor belt where it decides whether to shift it over or not shift it over. There's an inductive sensor right there too.
Why inductive? No.
Yeah, so what they're doing is they're sorting. When you get into the conveyor, the robot puts them together to difference from what they are. Now they could do that without shifting them, believe it or not. But Amatro, when we went to, I think I might have told y'all the story. When we went up there to Tennessee to do our training, the level 1 training, I brought it up. I said, guys, there's a lot simpler ways to do this than to put all this stuff on the line. And the guy, he told me, he said, Rich, he said, what they were trying to do is they're trying to put as much stuff on this line as they possibly could put, so the students could see all this stuff. So yeah, they didn't have to do that, but what they're doing on that one is they have an inductive sensor, and when the blocks come through, it's got a thing over here. If it's metal, it shifts it over to this side. And if it's acrylic, it lets it come straight through. And so it does that with an inductive sensor. It uses a retroreflective sensor over here to sense when the object gets there. So retroreflective to see it's there. And then it's got an inductive sensor that sets up there that tells it if it's what? Metal. If it's metal, then this guy will come out and shift it over here. And then if it's acrylic, it comes over here. And then it sends that information to the robot station, and the robot station knows which side to come and pick it up at. And then it knows what spool to put in there too, depending on if it's metal or acrylic.
saying that it doesn't sensor sending the information to the robot, it's another sensor when you get to the end of the line.
Yeah, over here it's got a retroreflective sensor. So if you look at it, it's retroreflective, so you'll see the light on one side and you'll see the reflector on the other side. It's a flat.
So retroreflective can tell it can tell distance, can it?
No, it don't need to tell distance, but this guy knows that it pushed that metal over there, so it knows it's got a metal one over here and acrylic over there.
So who's telling the robot which side? That's what I'm asking. I know that.
Well, it's whatever signal that sends this that pushes it over.
That's it. That sensor
Yeah.
the robot which side.
Yeah. Well, the signal from this sensor right here.
It didn't get a signal from there, and then it knows at the end, it knows it's over here.
Yeah.
It did get a signal from there.
And it's got a counter that goes on too, so it knows how many's down in the spool. So if you got a metal one and an acrylic, then the robot will start going back and forth, and it'll do a metal one, then an acrylic, and go back and forth. And it keeps up a counter. And every time the robot puts one together, it'll decrement the count, so it knows. We do have a little problem in the system though, but so the only thing we got to worry about on these solid state sensors, and basically we already know how we don't really need to know how an inductive sensor works, even though a capacitive sensor works, even though I gave you a little insight into it, right? All you got to know is capacitive sensors can be designed to detect almost what? Anything. And of course, the range depends on what it's trying to detect. So metals would be easier to detect because it would affect the magnetic field a lot, right? When you start getting into plastics and stuff like that, that could give you problems. So these guys might have sensitivities on.
Clarify this. On the carousel over there, those are passive.
Well, it's got a capacitive and it's got one inductive because
Well, I know, we can put our hands over there, you can see it. That's a capacitive.
Yeah, if it trips with you, and it trips at anything you put out there, then it's going to be a capacitive sensor. If it only takes.
Well, I guess I thought it got those little red lights or something. I didn't know.
No, we're thinking about something else. You're talking about those are reed switches or Holotech. And I think I told, huh?
The carousel goes around.
And then it's got the
When you index it, when you turn it off, turn it back on, it comes back to the same point.
well, it comes back to a point that's relative to the same. Y'all get me off on tangents all the time.
Does the capacitive sensor put something out? How do it know?
What do you mean, does it put something out?
Well, the capacitive sensor, is it shielded or unshielded?
Well, it depends on what application. Shielded is going to be more selective, right? You understand?
Right.
An unshielded is going to be less selective. I think the Amatrol line has shielded, and I think the Festo line has unshielded. I'm almost sure, I think. Because the Festo line uses an aluminum. Its carousel is aluminum. The Amatrol line, its carousel is steel. So that means aluminum would have a less effect on a capacitive sensor than, I'm sorry. Okay, so these are the Amatrol line. That's module 3. And so these are capacitive sensors. That's one there, we got one there, one there, and one there. I think there's one under here. This is the inductive sensor right here. So when you turn this thing off, what it does is it starts stepping in this direction right here, no matter where it's at. So we've actually played around with this, and we'll get it going and get it halfway in its turn, and we'll flip the dang thing off. and then we turn it on. And what it does, it starts stepping in the same direction. Starts stepping in this direction right here. And it waits for this output of this sensor to hold there, and it waits for it to go false. And then what it does is it steps it back so far, and then it knows it's lined up. That makes sense? And these are capacitive sensors, which indicates there's something there. So this is the first one it sees. And then it moves to this position, and it sees it there, then it moves to this position and sees it there.
Those will be shielded, right? Because he doesn't want them to shoot straight up.
Yeah, these are probably shielded because we want them to be more selective, but I'd have to go over there and actually look at them. We're going to try to make sure we get back over there when we learn all about these different sensors and go over there and look at them and see if they're shielded and unshielded and that kind of stuff. So you have to adjust these. You got several ways. One thing is you can adjust the height on them. And you saw that it's got the ability, that it's got threads. And what we do, of course, is we put we have a lock nut on one side, and then we have some type of mounting plate. And we have a lock nut on one side, and what we can do is we can move this back and forth, and we can adjust the proximity to what it's trying to measure. So the closer you get to it, the better it's going to be at measuring items. The further you get it away, the harder it's going to be. So you can literally make an inductive sensor ignore certain metals just by doing what? Backing it off away from them far enough. And that way it might just only sense steel and maybe not sense aluminum. If it always came back at a certain distance. So yeah, you can make these things selective by doing what? By adjusting how far they are away from where you're.
I think in the troubleshooting class, we changed one of those out. That's the one we changed out, the big round one.
No, that was an ultrasonic sensor.
But we adjusted the height of it.
Yeah, you had to calibrate it.
Yeah, we had to go over and do some stuff to turn it off and turn it back on.
Yeah, well, that thing was calibrated to see a high and a low.
But that wasn't a capacitor.
No, it wasn't a capacitor, it was an inductive sensor. I'm sorry, it was ultrasonic. Inductive sensors work it basically the same way, except their formula is just opposite. So on inductors, as frequency goes up, opposition goes up. Their opposition is called X of L, by the way. It's in ohms. But this is what determines it. So we got to put AC on these things. If you put DC on this, it's going to act like a straight piece of wire. This is why your stereo has to output AC, because if it didn't, your speakers would act like a piece of wire instead of working like electromagnet, like you burn your amplifier. The number of conductor loops, the proximity of the loops, the ferrous metal that the loops are coiled around, or placed in close proximity. But so what are we doing here? We're not changing the number of loops. We're not changing how close the loops are together. What we're changing is this guy right here, the ferrous metal that we're exposing these coils to. We change the ferrous metal, then we change X of L. If we change X of L, then we change the voltage drop, right? And then we can sense that voltage drop. Well, these guys, the sense element here requires AC, but we can power these things off of DC. Even if we power them up off AC, it's going to have to reconvert it and re-oscillate it to get the frequency that's required to trigger these things, right? You understand that? Well, these guys look for metals. And we look at them, if we look at them lay out, they look exactly the same as capacitive sensors. It's real hard to tell what they are just by looking at them. So you need to know the aspect or where they're at. A lot of them too, by the way, will have little indicator lights on them, which will indicate when they see what they're supposed to see, or when they output a true or output a false. On the black wire, right? You understand? So if what they see is true, then it's going to put a voltage output on the black wire, but on the white wire it would be false, right? Because it's a double pole, double throw. We see it as a double pole, double throw output, but it's actually usually transistors. I haven't seen these that have relay outputs. It wouldn't surprise me if they didn't, if they wasn't available. I hadn't seen them. But usually they have electronic outputs like triacs and transistors. So this basically shows how it works. It generates a magnetic field, goes out, we bring something in, it changes the core material, which is caused it to run. And it's got a lot of electronics in it, guys. I mean, there's a lot of electronics in it. I really like this. But you don't see that. All you see is the water. All you see is this right here. That's all you see. And then it comes out with wires, and it's up to you to identify the wire. If it don't follow the color code I told you, then you get the part number up and you look it up and see what the color code is. If it's AC, the color code probably don't make any difference anyway because it's water. AC, and AC has no polarity. But if it's a DC inductive sensor, like all ours over there, that means when you power that thing up, you're going to have to make sure you honor the polarities. All the ones we got over there follows the standard row of brown for positive, blue for negative, and black for signals. If it's 3-wire, if it's 4-wire, it's going to add a white wire. And the black and the white will always be for inverted. Yeah, good guy. So we looked at inductive, we looked at capacitive, we looked at photoelectric, we looked at the Hall effect, we looked at magnetic reed switches. We looked at photoresistors. I bought a photoresistor over too. I'm going to go ahead and pause this because